All right, now we're going to talk about a second version of the weak law of large numbers. The second version is a bit more general than the first. And let's see what it is. We'll call this the weak law of large numbers version 2. And let's suppose x1, x2 are IID mean mu. So we're not assuming a variance. So remember, it is possible for variance to be infinite. In the above, we assume that the variance was finite. So variance can be infinite in this case, but we still get the weak law of large numbers, convergence in probability to the sample mean. How do we prove this? Okay, so the proof requires a different technique now. The technique that we need is we need to use the moment generating function, actually. Okay, so in this case, let's note that Taylor expansion of e to the tx can be expressed for small t as ft plus tx plus tx squared over 2 plus some higher order terms that go to 0 faster than t squared. And this is as t gets smaller and smaller. So this is a little bit of notation that says that O of t cubed, O of t squared, goes to 0 at least as fast as t squared as t goes close to 0. So in other words, we can ignore it as we think about t getting smaller and smaller. So then for this case, what can we say? For sample mean written in this way, what do we have? Well, for the moment generating function of the sample mean, by definition, is expectation e to the t times the sample mean, which is expectation e to the t n inverse sum of the xi's. And so this is the moment generating function of a sum evaluated at t over n, right? So this is a product of moment generating functions and their IID, so it's an n-fold product. Oh, it's killing me. So t over n raised to the power n. Okay, so now what we want to do is use the Taylor expansion. And if we use the Taylor expansion, we can see that this actually can be written as the expectation of 1 plus t over n tx over n plus little o of t over n raised to the power n. This thing is really not cooperating right now. Okay. Well, how do we express this? This now is 1 plus mu t over n plus some negligible term as n goes to infinity. So we can ignore it, and then this converges to e to the mu t as n goes to infinity. Well, what is e to the mu t? Note that e to the mu t, or e to the t mu, is the moment generating function of the constant, the degenerate random variable. Oh, this thing just won't let me write right now. The degenerate random variable that is constant at mu. So we actually get by the uniqueness theorem of moment generating functions, we show convergence of the moment generating function doesn't require us to have a finite variance in this case, and we see that the moment generating function, as long as we have a mean, converges to the moment generating function of the constant at the mean, and that is what proves to us convergence in probability to the constant mu. So those are two different versions of the weak law of large numbers. And this really is, pretty weak assumptions. If you have a mean, if random variables have a mean, then if we have an IID sequence with that mean, then the sample mean converges to the true mean.